In this problem, we're told that a drug is used to treat leukemia, and we have the data on remission times in months for a random sample of 24 patients using the drug. Now, because we have less than 30 patients, we should actually know that the data is normally distributed, and it doesn't say that in the problem. So we're just going to assume that it's normally distributed here, but that was my fault. So it should really state that. So the question is, does this indicate that the mean remission time is different from 36 months using a 0.05 significance level? So first question is, what kind of test is this? What information do we have? In the question, we are told that there's a sample of 24 patients, and then we have the data on this. And we know that we're testing to see if the mean remission time is different from 36 months using a 0.05 significance level. So that's kind of all the number parts. But I look through here, is there anything that says anything about sigma, about the population standard deviation? Because we're talking about a mean, and so we need to know if we know sigma or not. And there's nothing about sigma population standard deviation. So the type of test that we're going to do here is a t-test. Next, we want to determine what are the null and alternate hypotheses. So we know that we're testing, or it asks, does this indicate that the mean remission time is different from 36 months? And that's what tells me what to do for the null and alternate hypotheses. So we want to know if the mean is different from 36 months, and that's going to be my alternate hypothesis. So I'm going to write H1, that's supposed to be an H, there we go, is that mu is not equal to 36. It didn't say larger than or smaller than, it just said not equal to. And so if that's the alternate hypothesis, then the null hypothesis is going to be almost the same, but it's going to be that mu equals 36. Okay? So now we've got our null and alternate hypotheses. Now we want to test this at the 0.05 significance level. So next thing I'm going to do is I'm going to put my data into list 1 in the calculator. So data needs to go into L1. And I've got my data in there, and now I can run my t-test. Now it asks for the degrees of freedom. So since there are 24 patients using the drug, the degrees of freedom we can compute by taking 24 minus 1, because it's always minus 1, and that gives me 23. And this is how you compute degrees of freedom for a t-test. Later on, we're going to do a chi-square test, and the degrees of freedom are calculated a little differently. So, so that's for this type is 23. Now, once I do that, I'm going to go into the calculator and do my t-test. And here's the result of that t-test. We have our test statistic is t, and that is 0.67. We're going to round the test statistics to 2 decimal places. And then we have our p-value, which is a probability, and we've been rounding those to 4 places. So that would be 0.5094. That's quite a large p-value there. And then they give us x-bar and the sample standard deviation, and we're not asked that, so that's all right. And n equals 24, which we already knew. So I'm going to fill that information in. And now I'm ready to form my conclusion. So, should I reject the null hypothesis or not reject the null hypothesis? So I'm going to take my p-value and I'm going to compare that to alpha. And in this case, the p-value, oops, I just did that exactly backwards, is greater than, quite a lot greater than, alpha, which is 0.05. So, p-value 0.5, alpha 0.05. So p-value is quite a bit larger. Now keep in mind, when you have a really large p-value, what this means, I'm going to just draw a really small distribution down here. You can draw the distribution with your calculator when you're running the t-test and get that result rather than doing the calculate. But we had a two-tail test, and so what you wind up with the results for that is that you have a lot of tail area here, right? Because this is taking up 50%. It's probably a little bit more than that even, right? So it's going to be a lot of space here. So what this means is that your test statistic, which we said was 0.67, right? So there's my test statistic, 0.67. And where is that falling as compared with the mean? Well, it's not falling that far away. Is it falling significantly far away that this would be a crazy, crazy answer to get? No. What we did was we said, what's the cutoff for crazy, crazy answer that, that would just not happen randomly? 0.05. And so that means 2.5% in each tail, right? 0.025, 0.025. So what happens is our p-value is much more than alpha. It fills in much more of the tail. So that forces that test statistic very close to where mu is. Now, is it forcing it? It's not forcing it. What we're saying is that because the test statistic is close to mu, that's going to define a very large area in the two tails. So it's not falling far enough away from mu in order to be significantly different from 36 in this case, because that's what we had for the null hypothesis. So we are not going to reject the null hypothesis. And so I don't want to reject it. So do I want to say that the mean remission time is different from 36 months? I do not. So I can say something like, there is not sufficient evidence to state that the mean remission time is different from 36 months. So we're not saying that the mean remission time is 36 months. Be very careful about that because we don't know that. We're just saying that we don't have enough evidence to say that it's significantly different from 36 months. And that's the end of that problem.